In my last video, I showed you how to recreate Kristof Dedene's cell shader using Python. In this video, we'll go one step further and make the setup a bit more user-friendly. I thought a nice feature to add to this shader setup would be to have all the controls for the shader in one place, so the user doesn't have to go through the nodes and set the attributes individually. The idea here is to create a group for the shader and add attributes that control the other nodes in the shader. First, we'll start by adding a new node tree on our material for the group. We do this by calling the new function on the bpy.data.nodeGroups object. The type will be a shader node tree, and we'll call it the Ghibli shader. For the nodes in our node tree, we'll need to refer to the group nodes rather than the material nodes, so we'll comment out our existing assignment to the nodes variable and replace it with a reference to the group.nodes instead. Now we're ready to add inputs to our group that we can use to control the various shader nodes. Since this is a multi-step process that we're repeating over and over, we'll create a new function to add the group controls. Into this function we'll pass the group, followed by the type of input we want to create, the name we want to show up on the group, and a default value. We'll also have two optional parameters for min and max values, which we'll need for only some of the inputs. We'll create each control attributes by calling the new function on the group's input and then setting the default value attribute. For inputs that use a float value, we'll set the min and max values based on what's passed into the function through optional arguments. This controls the range of values the slider uses when the user slides the control. We want to set this for float inputs because we wouldn't want the slider's range to be 1 to 1,000 if they only need to set values from 1 to 10. This would make the control almost impossible to use. So by defining the min and max values, we can manage this more carefully. This if statement will also apply the min and max values for the node socket float factor types, for when the range needs to be between 0 and 1, and in those cases just apply the function defaults. With our function in place, we can now add our calls for it for each of the inputs we want. We're creating inputs of various types here, which are mostly self-explanatory but worth going over briefly. The inputs will appear on the group in the order you create them, so it's worth planning out how you want them ordered. For my version, I went through Kristof's tutorial and made a note of the various controls in his shader that he used to change the look of the material, and then I added an item for those controls. You can control as many or as few of the shader options as you want, but these were the ones I chose for now. I started with two color inputs for the two colors that we use in the shader. For these, I used the node socket color type, and I used the names color A and color B for the names. For the color inputs, we feeded an RGBA color as a 4-item tuple with 3 colors in the alpha. Next I added inputs which we'll use to control the position of each marker on the color ramp. For these we'll use the node socket type node socket float factor, which defaults to a min and max range of 0 to 1. The next input controls the factor on a mix node, which also takes a 0 to 1 value, so we'll use node socket float factor for that as well. For our noise scale input, we do not want to be limited to 0 to 1, so we use the type node socket float instead. The rest of our inputs are of the node socket type float or float factor with one exception. The hatching scale takes the type node socket vector, which controls the scale on the mapping node, so for that one we'll pass a 3-item tuple for the X, Y, and Z scale. In addition to all the group inputs, we also need to add one output so that our group can output the results of the group to the main material output. We do this by calling the new method on the group's outputs. We also need to add an input and an output node to our group so that data can travel between the group and the various shader nodes inside the group. Although we've been working with a node tree for the group, we need to now create the actual group node by calling the new function on the node tree and creating a node of the type shader node group. Note that by referencing the node tree variable here, we are creating the group at the overall shader level and not within the group itself. After creating the group node, we assign the group variable to the group node's node tree. The group variable here refers to the node tree we've been building, so here we're effectively plugging in our node tree to our group node. Then we link the group node's output to the material output so that our group data is what gets rendered to the final shader. Now that we have the inputs set up on our group, we need to revise our links. There's a few things we need to address here. First, the main nodes in our shader now live inside a group, so we need to change our commands that create the new links to do so using the Groups node tree instead of the Materials node tree. This is pretty simple to do. We just append a group dot in front of each of our commands, which will cause it to refer to the groups links instead. The one exception to this is the very first link in our list. In our previous version, we linked the emission shader node to the material output node. But now that we have the group node instead, we need to change this link so that we're linking the emission shader node to the output of our group instead. Lastly, we need to link our group's input attributes to the inputs of the shader nodes they're meant to control. Linking these is exactly the same process as before, but where we call the new function on the group links and we specify the input on the target nodes as the first argument. But for the second argument, we refer to the input node's output that we want to link from. I know, confusing, right? But such is life in the land of nodes. You could think of it as we're linking the incoming signals from the group to the inputs of each target node, if that helps. The linking process we've been using works fine for controlling most of our shader inputs, but the color ramps are a bit trickier to deal with. This is because the little tabs we use to control the position and color along the ramps are not exposed to the inputs. So if we want to control them, we have to find another way to connect them. While the color ramp sliders are not connected by its inputs, they are accessible through the API via the color ramp node's color ramp elements list, with each tab on the slider being a Python object of the type element. This is good news in that it allows us to set the element's position, color, and alpha using Python. But the tricky bit is that we don't just want to connect the element. We want it to be controlled interactively by the attribute on our group. And to do that, we'll have to set up a driver. Drivers in Blender are a way to link one attribute to another via an expression so that they update in real time. Setting up a driver in Blender is a bit convoluted when you do it manually or by Python. But thankfully I found a generic function on Blender Stack Exchange that was posted by the user T. Lowski that does most of the heavy lifting. In this function we pass in a source, that is the attribute we want to drive, and in this case it's going to be the ramp element that we want to control. Next we pass in a target, which is where our driver is going to live. This will be our material. Next we pass in the property that we want to control, and on these ramps that will be either the color or the position. And after that we have the data path, which will be our group input, which will be driving our ramp elements. The index parameter is used when driving attributes with multiple components such as color, which contain values for R, G, B, and A, or for scale values which contain X, Y, and Z values. The final two parameters are for inverting our driver function and passing in custom functions. We won't be using these last two parameters, but we'll leave them in anyway. Inside our add driver function, we start by calling the driver add function on our source object with an if statement which uses a specific index if specified. We start by creating new variables for our Python objects, and then we set the name of the variable to be the property that we want to control it. In our case, this will be our color ramp element's color or position. After that, we set the variable target types to material and then the target and its data path. With our variables in place, we set up our functions using any custom functions passed in and our variable name. And finally, we set up the inverse relationship if it's set to true. This would be used in cases where you want the source property to go up when the target property goes down. Again, we're not using this feature in our script, but we'll keep it in there nonetheless. With our driver function in place, we can now add our calls to it further down in our code. Our first argument will be a reference to the element that we want to control on the ramp. We can access this by the color ramp's colorRamp.elements list. Each element on the ramp is referred to by its index. We only have 2 elements in each of our ramps, so the index here will be 0 for the first element and 1 for the second. For our second argument, we'll pass in the material. The third argument is the property on the color ramp element we want to drive. This will be either the position or color. The last argument is the data path that represents what we're using to drive our property, which in this case will be the inputs from our group. You'll notice that we're not passing in the input Python object here, but rather the explicit path to the group's input as a string. And that's because the path on the driver is expecting a string. And that should do it for our new and improved shader. If we run the script now, we would expect to see a group and a material node with all the other shader nodes hidden. I hope this has been a helpful tutorial. Thanks for watching.